Welcome to my talk about open source software, weaponized as part of a compromise. Few things first. I always tend to start my presentations, especially as I work in Accenture, with disclaimer that this presentation solely is presented by me, created by me, and all the comments, stupid jokes, etc. are on me. So if you are going to sue someone, sue me, not the Accenture, please. All right, so who am I? So my name is Jauhiainen. I'm from Finland. This is my third time speaking in B-Sides Dublin. I have been working in the information security for almost 11 years, mainly doing DFIR, slowly pivoting to the CTI, malware analysis. My background, I have a master's degree in cryptography and information security, and I do a lot of community stuff in Finland. So if you are ever planning to come to Finland, I suggest, for example, participating in Disobey, which is a security conference, or Hellsec, which is like B-Sides, but we host it a little bit more often. I also have some military background, so doing participating in Locatilds every year since 2018, and and part of that, the tweet there by Finnish Defence Forces. I heard recently that it's the most popular social media post of Finnish Defence Forces ever. So I wanted to add it to my CV because why not? All right, so that's enough about me. So let's go to the actual topic today. So what we're going to see today, first I'm going to introduce you a case where I got familiar with the malware. Then the actual malware analysis, and then the case summary. So what we learned from this case and what could be improved and so on. So let's start with the case introduction. So this case started around early December last year when the client engaged Accenture to help them with the incident response case. And I will walk you shortly through what happened actually. So basically, it started with the threat actor forking the real KeePass software. So as you may know, KeePass is open source software. So this source code is available and they can copy it, make their own version and publish it. So they did that and added few extra features to the code, which I will show you later on this presentation. Then they created a fake website which mimics the real KeePass website. So this is typo-squatted domain, keycast.com, where they were sharing their own version of the KeePass. And of course, they wanted users to find their way to this website, so they started an advertisement campaign on Bing search engine. And now the actual victim comes to the play. So one of the employees of victim was using KeePass on their daily operations. They were working in the social media team of the company. They were using the Windows Cortana search bar, the search bar on the bottom left corner of the Windows taskbar to search for KeePass. And unfortunately, the Cortana search bar also shows you ads. It doesn't show the real results, but it also shows the ads, which in this case were set there by the threat actor. And they ended up downloading the malicious version of the KeePass. The KeePass launches, it does several other things as well, but it launches Global Strike Beacon. And later on the same day it was launched, the threat actor started their manual operation on the client environment. So a little bit about the case. So the client had Microsoft Defender for Endpoint installed. The incident was detected quite fast. So basically the first alert came 6 hours after the installation, around 30 minutes after the manual operation of threat actor has started. the MD alerted when the attacker executed another instance of the beacon. So basically, they were operating manually in the environment. They didn't use the initial beacon, but they launched another process of Cobalt Strike, which then was detected by the MD. So the first execution was not detected by the MD, and the threat actor had around 30 minutes to play in the environment. So no detection or prevention of this key pass, and based on my knowledge, this key pass version can still be installed and executed on systems running MDE. The binaries in this case were retrieved using the EDR, but they are and were available in VirusTotal as well, so someone else had seen them as well and uploaded them to the VirusTotal. So let's start the malware analysis. So first, of course, I downloaded the executable, the installer file of the KeePass, and took a look how it looks. So first of all, the binary is signed. So the client actually said to us, all right, you got it anyways. So the client said to us that this looks like benign binary because it's signed and it says on the company the original developer name of the KeePass. But here are some things that are odd. For example, the company, the publisher, Avarcom LLC, which we'll discuss later on a little bit, but it doesn't sound the company that actually is releasing KeePass. It's something else. So basically, stolen certificate for doing the digital signature of the binary. So, and also other thing is funny that the name of the file was KeePass 2.57, but the actual product version, which is visible on the setup, is one version before. So I don't know what the threat actor did. Why did they mismatch version number there? But this is something. This is a red flag basically, and we need to analyze more what the actual installer does. But this installer is built with the same setup tool, InnoSetup, as the original version. So it's really easy to extract and see the contents. What are the files inside of the setup? Because I believe that all of the files are not on VirusTotal, so you could not download them one by one. You have to download the bundle to analyze all of the files. So what I did then, of course, I wanted to go and compare them to the real version of the KeePass. So what is different from the real version, and what are the same binaries? And immediately on this, I saw that most of the files installed with the KeePass installer, the malicious version, are the same, except the keepass.exe, conf.bin, and shinstutil.exe. And this conf.bin doesn't even exist in the real version. So these were definitely point of interest here, event of interest. What are these files doing? And then I started the analysis process. And I will skip a little bit because I don't know how people usually analyze malware, but for me, it's frustration of hours, and then I finally get results, and then I go back to my analysis notes and see what I actually found. So a few moments later, I will skip the part of frustration because I cannot fit that to the 25 minutes. But the overview of file, so basically the KeePass setup installs the three important files to the disk. So the mentioned keepass.exe, shinstutil.exe, and conf.bin. And these three files are definitely malicious, and I will shortly explain what they are doing. But the keepass.exe was .NET binary, shinstutil.exe was traditional C binary, and the conf.bin was encrypted data, so it wasn't anything clear text. You could identify what the file is. The infection chain is so that the keepass.exe launches the shinstutil.exe that decrypts and executes the Cobalt Strike beacon from the configuration file. And of course, before going to the decompiled code, I want to show you how the program actually works. So it works like the real KeePass. So basically, the user can use it for their password vault. And this is a screenshot from my lab where I installed the malicious version and created this passwords.kdpx, database.kdpx, to store my super secret passwords. Then I checked with the process monitor what's going on there, and I saw that it's writing this suspicious file to the app data local directory named 3 digits and KP. Of course, I wanted to know what is there. Boom, there is my clear text password. So basically, it's information stealer. So it steals all the credentials stored to the KeyPass database and writes them to the file. So let's take a deeper look how this actually works. So this main form class of the KeyPass.exe has actually almost 200 lines added. So there is some additional functionality which is not in the real KeyPass. And if we take a look what it actually does, it basically loops through the database and steals the important and relevant information there. And in the end, it writes them to the file, which is located in the user app data folder, and names the file with three random digits .kp. So we already knew that. But it also has some other functions. So, and one important point from this one. There was this if condition. So if the user has 8 or more passwords stored to the KeyPass vault, it would do the execution and write the files to the disk, the passwords to the disk. So if the user had, for example, 6 passwords, it never did anything malicious. So I suggested, well, it's a joke, but I don't know if the client understood it, but I said that if you had less than 8 passwords, you're safe because it doesn't do anything malicious and you can continue using it as it is. So the other function is launching the sh-institutil.exe, and it gives to this executable this kind of hexadecimal parameter as well. And it started with that one, and it also sets a persistence for this executable. So every time the user logs on, this executable is executed with this specific parameter, which is this kind of like hexadecimal string. And my question was, of course, first of all, what is this sh-institutil.exe actually? What is it doing? Because it was visible on the real KeyPass version and also on the malicious one. And the other question was, where is this hexadecimal string used? So what is the sh-institutil.exe? So in the real KeyPass, it's the shell install utility. So basically it helps the user to open the KDPX files with the right click, open with KeyPass. So basically it implements this. And in the real version, there is only 2 parameters. There is install and uninstall. So it doesn't have this kind of query parameter. So of course, that was my point of interest when I went to the compile code and see what it does. So I saw that in the main function, it first checks if the query parameter is given to this binary. If the check is passed, it will load the content of the conf.bin to the memory and then use the parameter query key as a key for RC4 decryption of the conf.bin, which is Cobalt Strike Beacon. Then for the execution, it doesn't launch it directly, but it uses enum fonts white character API as a callback function. So basically, it enumerates the fonts on the Windows system, and when it completes, it doesn't return to the sh-institutil.exe, but instead launches the Cobalt Strike Beacon. The next step, of course, is to decrypt the actual content of the conf.bin to see what kind of Cobalt Strike it is and so on. And I'm a very lazy person, so of course I prefer to run things than write my own decryptor for the configuration files. So basically what I did, if you've ever done malware analysis, you are very familiar with dumping stuff from the memory to the disk for analysis. So here's just walkthrough. So basically checking where the actual content of the config is written in the memory, then waiting it to be decrypted, and then dumping the decrypted version of the shellcode to the disk for analysis. And as I already told, it was Cobalt Strike. And if you have ever done DFIR, I guarantee that you are seeing a lot of Cobalt Strike. So this wasn't anything like surprising or anything cool. But this basically is day-to-day work if you are doing DFIR, analyzing the beacons. But let's take a look a little bit to the beacon configuration. So the Cobalt Strike beacons always have these license IDs. So they are trying to say which license was used in the team server where this Cobalt Strike beacon was generated. In this case, they're using license ID, which is publicly attributed to Black Pasta. This is not attribution, but I'm just saying that the Black Pasta group has been using the same Cobalt Strike license. Of course, it might be a cracked version, but usually if you are looking at the Cobalt Strike licenses for cracked versions, it's something like 1337 or 1234 or 6666 or something. And in this case, it looks like a real license ID. Then if you look at the C2 domains, the callback domains where it actually calls, these are similar to the domains that Black Pasta has used in their previous operations. So yet another strong, well, I wouldn't say strong, but indicator leading to the Black Pasta ransomware group. But I'm going to tell you why this case didn't look like ransomware or Black Pasta. At least what we saw in the case. The funny thing about the domains, if you have been analyzing malware, you often see that the malware is using the same protections for their C2s as the companies are using for their own websites. And in this case as well, they were protected by Cloudflare. I'm very sorry if someone is here from Cloudflare, but I have had a lot of problems with you previously in takedown requests or getting more information. I'm just asking, why are you protecting the criminal activity? Why are you protecting their infra? All right, let's move on to to take a look for the other artifacts related to this campaign. So first of all, the job site. The keycast.com wasn't the only site they were advertising. There was several others, and there are still several other sites. So here is the list I identified a few months ago, which were giving the same, sharing the same kind of binary. So they were not just using one domain, because if one is taken down, then the other one can be used and so on. But this was very effective back then because a lot of companies were searching KeePass from the Bing and ended up downloading malicious version. Then a little bit about the digital signature. So like I said, the company name Avarcom LLC does look a little bit suspicious, especially if we compare it to the real version, which is signed by the open source developer of the real KeePass. And I did some searches on the Avarcom LLC, but I couldn't find anything else than two companies. One of them is based in Uzbekistan and one of them is based in Russia. So if we think this is yet another ransomware campaign, the companies are located in the countries which support our theory as well. Then the other thing, if I was looking, if the same digital signature is used for other malware, if we can find any other binaries in VirusTotal, so if we can see any other campaigns or any other open source software they have weaponized. But unfortunately, the only results were the KeePass files, which were analyzed in this presentation as well. Another thing which I'm looking for is the debug file paths, which are found from the executables, and they don't give that much information about the original developer. But of course, if we are seeing the same path in the future as well, we can attribute the new malware to the same threat actor. The same threat actor had similar campaign last summer as well. So they were using the same beacon similar way to compromise systems, but they were using different open source software. They were using fake advanced, well, it wasn't open source software, but different software. They were using fake advanced IP scanner, which I think wasn't that successful because typically the normal people working in the organizations don't use IP scanners at their day-to-day work. But in this case, instead of implementing the information stealer to the actual source code, they were actually using DLL sideloading to execute the malicious version, the decryptor of the global strike. But they were using exactly the same beacon in this campaign. So let's move on to the case summary. So, low confidence attribution to the ransomware group. We are not sure if it was a ransomware group, but there are a lot of things that suggest it was. The weaponized key pass was able to steal credentials there, and they were using malvertising and required user activity to launch this campaign. The biggest question of this case is why Windows 11 is showing the malicious ads in their Cortana searches. And I don't have answer to this, and I'm sorry if you work for Microsoft, but you can ask this internally, why we're doing this. This allows attackers to do a lot of malicious stuff for the regular users. And then we come to the impact. And as I said, no ransomware in this case, so I have to prepare you for the disappointment of the century. So let's repeat. No lateral movement, no ransomware, no additional malware deployed, and only key pass credentials were compromised. So what did they do? They got credentials, and as I said, this person was working in the social media. They launched a crypto scam website. So they got access to the key pass credentials. They read the credentials, and after that, they got detected. So they had to pivot from their initial access somewhere else. So they had the access, they were kicked out, but they still had the credentials. So what they did, they created NFT-themed website with the client. They basically used the client's website to do that. So basically they copied the graphical interface of the website, like the layout, and created own website where they actually implemented this kind of crypto wallet stealer. So if you browse the site and run the JavaScript and you have session open to, for example, Coinbase or something, it will steal your cryptocurrency there. And then they promoted the website using the victim's social media. So as I said, they stole the credentials. They had access to a Twitter account, which had over 500,000 followers. So the reach was really big on this case, and it actually was in the news in the country where this actually happened as well. So they potentially, I haven't followed the cryptocurrency, wallets, so I don't know if they actually succeeded stealing money, but there's a big chance they did. And one of my biggest worries is that if the MDE did not detect the another beacon launched in the environment, would the incident have led to ransomware? And I don't know. I can of course speculate that it could have led, but in this case, the Microsoft detected the beacon and the incident was contained. So what are the lessons learned from this? In this case, we were actually faster in the malware analysis than doing the forensics. So when we actually got the laptop of the user and did the imaging process for it, we already had completed the malware analysis. So we exactly knew what happened in this case and what is the chain of infection. Of course, we had to verify those from the disk as well so that we can see the drop sites and so on. The credentials for the social media were shared among the social media team. And of course, they didn't have MLA. So when the threat actor got the credentials, they were easily able to log on to the social media and use Twitter account as they want. And of course, the last one, should the users be able to download software from internet? And this is like a continuous discussion with multiple organizations. Why the users are not provided with the software they need to use, why they have to go online and download the file, and why they are able to install those. So should the, for example, application whitelisting or something be implemented in the organization? And this ends my presentation. So thank you very much. And if you have any questions, I'm happy to answer. All right. There's one. So what tools I use for analysis? So I'm heavily relying on IDA Pro still, even though that it's very expensive. As long as Accenture pays my license, I'm happy. But I'm thinking to move to something more less expensive. For example, the Binary Ninja, I have really good experience from that. On the .NET side, I think I was using ISPy instead of DNSPy, and then some like Microsoft native tools like from the internals for the SyncCheck and the, of course, the InnoDB. It's an open source extraction tool for the InnoDB build tools. But that's about it. And of course, x64 DBG for debugging. There's another one. Do I know why MBE failed to detect that? This is the third time I'm giving this presentation, and I've been always asked that. And I'm still investigating that part. I don't know why. I don't know the answer, but it's interesting, like why it didn't identify the cobalt strike. You can inject it to the SH study. Alrighty, there's one more. Sorry, I cannot hear you. Can you come forward?
3 questions. The first one's kind of a light-hearted one. It's probably Juho Gonzalez. Is that your pseudonym?
That used to be my pseudonym. So there's a story. I can tell when we have pints about this, but it's now burned, so I cannot use it anymore.
The second question then, what responsibility do users have in terms of
So can we go? So what responsibilities who has? The vendors. In this case, you mean like Microsoft or Cloudflare? Or yeah, that's a great question. I think. I think Google is nowadays really good at blocking malicious ads. There is not many of those, but Bing, no. So I think they should be responsible for that, but that's my personal view. I will unplug my computer. I will come there so we can continue. It's really hard to hear here.